Boop, 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 boop. Okay. So previous units we've been talking about what goes on in the middle of the atom with the nucleus and the protons and the neutrons. And now we're going to talk about what goes on the outside of the atom, and that would be the electrons. This is kind of an interesting series of letters and numbers. I want to read it to you because it's pretty important. It's called an electron configuration, and it's read this way: 1s2, 2s2, 2p6. It's not read 2s squared because this is actually not a mathematical function. It is an address. It's an address, and you're going to learn about that address later on. But right now it's read 1s2, 2s2, 2p6, and so on. Okay, so we didn't learn about atomic history because someone decided that you didn't have to learn about atomic history anymore. But I just want to shed a little bit of light on the situation because it's relevant to what we're doing. About 120 years ago-ish, basically the beginning of the 20th century, we used to think atoms were like a BB in a beach ball, or if there was a BB inside this balloon, where the BB in the middle would be the nucleus, and then the electrons would be zooming around on the outside. That worked pretty well for our models of understanding. But then there was this guy who came along, and his name was Niels Bohr. And he discovered something kind of interesting. He discovered that electrons don't all exist in one big shell, like a beach ball. He found that electrons exist in energy levels, like an onion. So like an onion has energy levels. And I do need a volunteer. I need a volunteer. Okay, perfect. Lane, come up here. This is going to require you to move around, and I'm going to put you on camera if that's okay. All right, so I'm going to twist this around so we can see what Lane's doing. There we go. Okay, so Lane, don't be scared. Don't be frightened. This is what I need you to do. I need you to stand right there for a second. Okay, so Lane is currently in the lowest level he could be on. He's on the floor, okay? And we're going to call the floor the ground. So Lane is currently on the ground. Are you on the ground?
Yeah.
Okay. This is what I'd like you to do. I'd like you to step up to the chair. We're going to call the chair level 2. Go step up to the chair. Okay. Now he's at level 2. He was previously at level 1, the ground. Now he's at level 2. What did his muscles have to do to get up to level 2?
Use energy.
They had to use energy. So his muscles had to use energy to get to level 2. Okay, now Lane, go up to level 3.
Is it safe?
This is very safe. Oh no, I'm just kidding, it's fine. So now he's on level 3. Okay, his muscles had to use energy to go from 1 to 2. Does his muscles have to use energy to go from 2 to 3 as well?
Yes.
In fact, it's actually a little bit higher. His muscles had to use a little bit more energy. Now, it's conceivable then that he could have, with enough energy, jumped all the way to level 3 from level 1? Well, electrons do the same thing. Electrons can jump between energy levels. They can go from level 1 to level 2, level 2 to level 3. Sometimes they even go from level 1 to level 3. But in order to do that, they have to do what? Get energy. Exactly, they have to get energy. They have to get what we call excited. Okay, now Lane, here's the tricky part. What I would like you to do is stand somewhere between level 3 and level 2. Stand somewhere in between. Okay, now you're on level 2. Can you stand right here? Can you stand right here? Yeah, like right in between. Now you're on level 2 again. Now you're on level 3. Somewhere right in between. Can you do that? No, and neither can electrons. Okay, thank you, Lane. Thank you. Well done. It's like, I'm so confused. Okay, yeah, so electrons can't do that either. Go ahead and have a seat. Thank you very much. That's okay. We'll clean it up later, or not. Someone else will rub it in with their elbows. Okay, so electrons do the same thing. They exist in levels, very specific levels, and there are 7 of them. But they can't exist in between levels. They can exist at level 1 level 2, level 3, but they can't exist in between. So I'm going to draw some levels. I'm going to draw some. I don't have a good dark pen, so let's see how this works. I'm going to draw. There's level 1. There's level 2. There's a level 3. I'm sorry, it's not very dark. There's level 3. I know.
I have a dark marker.
You have a dark dry erase marker?
Yeah.
Lay it on me. Excellent. Okay, so there's level 1, and there's level 2, and there's level 3, and there's level 4. Excellent. Thank you very much. Okay, so you got an electron, and it's hanging out at level 1. There's an electron. It's hanging out at level 1. And it can do various things. It can jump between levels. Now, I've only drawn 4 of the 7 levels it can jump to because I don't think we need all the rest of them. Quantum science is the study of this idea that the electron can take in and give off energy of a very specific size, a little packet, if you will. And quantum is a packet. A single quantum is a single packet of energy. America.
Okay, so I learned that there's like other ideas about the electrons and something called a cloud.
Mm-hmm.
Like, would they still jump for different levels
Mm-hmm.
of the cloud?
Yes, and very good point. Okay, so I'm going to treat electrons like they exist like a thing and not a phenomenon of energy. Okay, so if you move on past the Bohr model, which is what we're learning today, you're going to learn about things called wave equations, where the electron is treated less like a thing and more like a probability of energy, an existence, if you will. But we're going to think of it as the wave equation. Yeah, we're going to think of it as something like a thing. Okay, so a quantum is a packet of very specific size. When you buy Skittles, you buy a quantum of Skittles. Okay, so the machine that dispenses the Skittles into a little Skittle bag dispenses a very specific number into each bag. It would be very strange if you had a Skittles bag where one had 100 Skittles, one had 50 Skittles, one had 1,000 Skittles, and one had 4 Skittles. That'd be very, very strange. So they have a computer dispensing a specific number of Skittles into the bag, and that number is a quantum. Similarly, electrons take in quantums of energy. So the levels between, or the energy between the levels is a very specific amount. So what is the amount of energy between level 1 and level 2? Just throw out a number. 5. Okay, 5 is a good number. So there's 5 in between level 1 and level 2. How much between, oh, by the way, I'm going to number these 1, 2, 3, and 4. How much energy between 2 and 3?
10.
10. Okay, that's easy. So 10 units between 2 and 3. How much between 3 and 4?
35.
35. Okay. 35. That makes it, that's a good broad number. Okay, excellent. So those are the energies between the levels. Now, if the electron absorbs 4 units of energy, guess what happens? It starts with an and ends in thing. Nothing, exactly. Nothing. If it takes in only 4 units of energy, it doesn't have enough to jump to the next level, and nothing happens. If it takes in 5 units of energy, if I give it plus 5, then it will jump from 1 to 2. And it will end up here, and it's going to be a word we call excited. It will be excited. Yay, I got energy. I'm excited. Okay, does that make sense?
Yes.
Now here's the cool thing. It doesn't stay there for very long. Once it's been excited, in an infinitesimally small amount of time, it comes back. And it loses that 5 units of energy. Now it's not sad, it's just ground. It's the ground level.
It's grounded.
It's grounded, yeah. Okay, so if it takes in 5, it goes up 1 level. What happens if it takes in 7 units of energy?
Then it'll go back because it can't stay little.
Right. If I give it 7 units of energy, it's going to jump to there. Is it going to end up somewhere over here?
No.
No. If I give it 7 units of energy, it's going to lose 2. 2 losed. It losed 2. Okay? In other words, it's only going to use the 5 units it needs. If I give it 7, it's only going to use the 5. The other 2 it's just going to let pass by. If I give it 9, what level is it going to end up at?
2.
It's still going to be at level 2, and the other 4 are just going to pass by. But if I give it 12, guess what happens? It still goes to level 2, because 12 would require how much energy? 15. So if I give it 15, then it's going to jump all the way over here.
This makes sense.
Yay! Making sense is what I'm going for.
So while all this is happening,
1 then 2.
while they're switching levels, it's going around.
Yep.
Okay, so those electrons that pass by, those don't get used by anything, right?
No, they jump up and then they jump back down. So they get excited and they return to their ground state. So if I give it 35 units of energy from level 3, then it can jump to level 4. So I can give it 35 at this point, and it will jump all the way to level 4 and be excited, just like it was in level 3. Does that idea make sense? Now, because you're smart, you can realize that once it's at level 4, it has some options. It can jump from 4 back to 3. It can jump from 4 back to 2. It can jump 4 all the way back to 1. It has options.
So it doesn't need to gain more energy to go back?
Okay, so there's all these crazy combinations it can jump up. If you give it an amount of energy between a level, it'll jump up. And then it can jump back down. If I give it 5 units of energy, it's going to jump to level 2. If I give it more than 5, but not enough to get to level 3, it will only jump to level 2. If it's at level 2, and I give it 10 more, it'll jump to level 3. But if it's at level 1, I'm going to need to give it 15 to get to level 3. I guarantee it, this is as complicated as the math gets in this unit. It's just arithmetic. Okay. Does that make sense, this general idea?
Yeah.
Okay, so those people who like to watch things on the PowerPoint, this is what's going on. You got an electron in its ground state. And you give it some energy. It absorbs the energy, forcing an electron to jump up into an excited state. It doesn't spend much time up there. In an infinitesimally small amount of time, that excited electron will return to its ground state. But what has to happen for it to return to its ground state? It has to lose that energy, exactly. And it loses it in the form of a photon. Photon. A photon is a light quantum. It's a light quantum. A photon is a packet of energy in the electromagnetic spectrum, which we're going to talk about in a little bit. But it's a light photon. Pew pew pew. So it's like Star Wars, like pew 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 pew. Little photons popping out. Pew, pew. Now, why is this useful to us? This is hugely useful to us. In fact, the technology that allowed us to take advantage of this, or the technology this takes advantage of, is actually fairly new. We've known this has been going on for 120 years, but the technology is actually pretty new. When I was growing up, if we wanted to make light, we had two options. One was to take a little filament in a glass globe and turn it into a tiny toaster. You know what a toaster does, right?
Yeah.
Electricity runs through a little wire, and the wire gets so hot it glows. Well, that's basically what an incandescent bulb is. Those old bulbs are called incandescent. It's basically a tiny toaster. There's a little metal filament, and we run electricity through it until it gets really hot and it glows. The problem with an incandescent bulb is if you had a pie chart of all the energy going in, very little is light, and most of the rest is heat. Okay, so imagine you had the bulb, and you had the little thing right there. So most of it is heat, and very little is light. In fact, there were buildings not 50 years ago who heated they heated their building with lights. The lights had to stay on all night because it was the lights that did the heating. Isn't that weird? Yeah. You're like, we're wasting electricity. This is how we heat our building. Okay, so very little of the actual energy turned into light. Most of it turned into heat, which is a huge problem in the desert because if you use incandescent bulbs in your house, you have to pay for the electricity twice. Once to make the heat, and then what else do you have to do with the heat? Once to get another time to get rid of it, exactly. So it's a big deal in the desert, which is why my house is almost entirely LEDs. I love LEDs. Okay, so I'm not talking about LEDs yet. So then we had these fluorescent tubes, and the fluorescent tubes had a gas in it, and we ran electricity through the gas, and what happened, guys, what happened is as the electricity hit the gas molecules, the electrons in the gas molecules jumped up. We were giving them quanta of electrical energy, and they were giving out quanta of light energy. This is how the fluorescents work above you. So basically the gas molecules took in light energy and took in electrical energy and gave off light energy. Pretty cool. And a lot more efficient. So if you did the pie graph, the same pie graph with the tube, you'd get a lot more light. Actually, it's closer to this. You'd get a lot more light and a lot less heat. Okay. That's for gas molecules. And then someone said, if we can use gas molecules in the gas phase where the molecules are really far apart, what if you had the molecules really close together in a solid? And that's where we get our LEDs. So an LED is called a solid state device. And basically how an LED works is you have the electrons and you have a material that absorbs the electrons and basically packs them full of electrons. And then they do a red rover, and they launch out photons as fast as they can because they have too many electrons. And if you were to, this is the LED, if you were to draw the pie graph for LEDs, it would look something like this, where this is light and there's very little heat. So lots of light, very efficient. You get a lot of light out of an LED. And that's what's going on in these LEDs. So I got some LEDs here. I got a red LED and a green LED and a blue LED. Then I also have a white one, which sometimes works. But the white one's actually less relevant to what we're talking about. So here's my LEDs. Yay! Oh, by the way, also the same phenomenon as the LEDs, lasers. Lasers are like the pinnacle of efficiency. The problem is the technology is still a little difficult to do. But there are actual televisions that use lasers to paint the picture. But the technology isn't very good for playing Xbox because they're too slow right now. The computers paint the picture too slow with lasers. But that's what's going on. Okay. Yeah. So, a little bit of lingo for you. The word is atomic absorption. The atoms are absorbing energy. And then atomic emission. They are emitting energy. So atomic absorption happens when the atom absorbs quanta of energy, and atomic emission happens when they emit or release quanta of energy. I love this animation I stole off the internet, because it's got a little blue cartoon and a little green guy and an orange guy and a red guy.
They make rainbows.
Yeah, they make rainbows. Well, what they're representing are different photons of energy. Different photons of different color or frequency carry different amounts of energy. That's fine. Just as long as nobody else realizes it. I don't want to have your parasympathetic nervous system blowing up on me. It's a thing that makes your nose itch when somebody says, "Does your nose itch?" It makes your nose itch. So, yeah, so like look at somebody's nose and ask them if their nose itches. Yes, I see you now. Okay. Yeah, some people are like, shoot, it does. Okay, so different amounts of energy produce different frequencies and wavelengths of photons. So in our little animation, the red guy is going bounce, bounce, bounce. He doesn't look very energetic. It turns out red photons don't carry a lot of energy per photon. Whereas the blue guy's going bounce, 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 bounce. The blue guy's got a lot of energy. He's carrying a lot of energy per photon. And that's what would happen in our scenario over here. I got my violet, got my red, got my green, got my blue. All right, so you're still scribbling. Wait till you're done scribbling. Most important thing is light energy toward the bluish side of the spectrum, of the light spectrum, or the rainbow, tend to have higher energy than those things on the reddish side of the spectrum, or the reddish side of the rainbow. Now wait a little bit while some of you are still scribbling madly away. All right. Okay, back to our scenario here. If an electron in level 2 jumped to level 1, it's going to give off 5 units of energy based on our scenario, right? So remember, this is 5, 10, 35? So that's going to give off a red photon, which is not very energetic. It's just got 5 units of energy. On the other hand, if an electron jumped from level 3 to level 2, it's going to give off 10 units of energy. It might make a green photon. See where this is going? And if it jumped from level 4 to level 2, it's going to give off 35 units of energy. It might make a blue photon. So far, so good? And maybe it's going to jump from level 4 back down to level 2, giving off 45 units of energy. It might make a purple photon, or a violet, or an indigo photon. Okay? Because violet has more energy than blue. And what if it goes from level 4 all the way down to level 1? How much energy? It's going to give off 50 units of energy. It might make an ultraviolet photon. We can't see ultraviolet. We can't see it. Some bugs can, some birds can, but we can't see it. An ultraviolet photon has even more energy than a blue photon or a violet photon. Okay, does this idea make sense?
Yes.
Okay. So we're talking about the electromagnetic spectrum here in a second. Okay, questions so far? Question in the back.
With the wave things, once they jump, is the only way they can go back, or can they jump more if they got more energy?
They can absolutely jump more. They can go jump, 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 jump. So they have the capability to go jump, 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 or jump. It's just randomness whether they do it or not. Okay, so this is our electromagnetic spectrum chopped into little pieces. This is all of the light that we can detect. It's all light. Now, what we usually call light is this tiny little slice right there. This is visible light. Tiny slice. Red, orange, yellow, green, blue, indigo, violet. Things that are more energetic than we can see are ultraviolet, X-rays, and gamma rays. And things that are less energetic than we can see are infrared, microwaves, and radio waves. Just like there is light bouncing off of the screen being projected from this projector, there is light coming out of the phone in your pocket. The only difference is the light coming out of your phone in your pocket uses uses radio waves. So the radio waves that are coming out of your pocket are right about here.